Hi, everyone. Thank you for joining us today. My name is Nicole Suri, and on behalf of MEGIN, I'd like to welcome you all to this MEGIN Masterclass with our guest speaker, Alex Gramfort. Just before we start, I'd like to ask attendees to please use the Q&A button on your screen to send in any questions you may have during the masterclass. There will be time for our guests to answer questions at the end of this masterclass session. This webinar will be available to watch on demand on the MEGIN website at a later date. So it gives me great pleasure to hand over to our guest who will officially kick off the webinar. Thank you.
All right. Hello, everyone. Thanks very much to MEGIN for organizing this presentation. This presentation that we'll be doing on MNE-Python and its broad ecosystem. So I'm Alex Gramfort, and I've been at the origin of MNE-Python now almost 12 years ago. So let me dive in by first show you basically the front page of the MNE-Python website. So you should just go to mne.tools, give you a glimpse of what you can actually do with MNE. You have an illustration of source estimation, machine learning. We'll talk about this a bit later, encoding models also, but many more. I encourage you to visit this website during the presentation or after if you have not done it. So MNE allows you to do many things. This is just a few eye candies, pictures of the types of output that MNE can offer you. There's a strong focus here on source estimation, but I can, and I will mostly highlight center space analysis today due to the time constraints. So very importantly, I would like to stress this from the start, is that MNE-Python is very much a community-driven project where a lot of people have helped over the last 12 years. I counted before doing the presentation, there's more than 300 people that have actually wrote code and shared code with the MNE-Python community and the MNE-Python code base. And feel free to see if you see any names, if you recognize any name in this slide. So MNE also has been funded through different sources. Historically, a lot of the NIH and the NSF in the US was funded by an ERC grant, which I had a few years ago in Europe, but also by the ANR and other sources of funding. And typically also some private support through the Google Summer of Code project, grants from Amazon Web Services or the Chan Zuckerberg initiative, CZI, that funds still currently some development in MNE-Python. A number of institutions have also participated through their employees to the efforts behind the MNE-Python project over the last few years. So let me start by some background. Basically, MNE-Python did not really start the MNE story. The MNE story was started now more than, let's say, 21 years ago, actually, by Matti Hämäläinen when he joined the Martino Center in Boston. And I joined the team of Matti in 2010 for a postdoc funded by NIH. And this is when I started the MNE-Python project to, at first, extend the C code in the MNE project, and before now being a total replacement of what the C code historically provided, and a lot more things. So MNE-Python is obviously written in Python. Python is a very now famous language that has kind of taken over the world of data analysis and data science and machine learning. MNE-Python is BSD license, which means that you can use it even in a commercial product. It's completely okay to do this. And it's a pure Python code, which means that it runs very easily on any operating system from Mac, Linux to Windows machines. Just to give you a few numbers that I found the PyPI stats website to prepare this presentation. MNE had been downloaded 1,700 times the day before I did this slide, 11,000 times the previous week, and 50,000 times the previous month. So if you have never installed MNE on your machine, you can do this by using the nice installers that Richard Oceanberger did while he was working in my team as MNE engineer, and that simplifies greatly the onboarding of new MNE users. So I encourage you to give it a try if you're especially new to Python. If you need help, there's also a nice forum that was set up. So if you go to mne.discourse.group, this is where you should ask your questions. And the hope with this forum is that the knowledge is actually disseminated, shared, and also questions can be answered broadly by the community and not only by the historical core developers of the project. All right, MNE is built on top of the scientific Python ecosystem. So what does it mean? If you understand a bit what the Python programming language offers, it offers fairly, I would say, low-level things, which historically have nothing to do with numerics or data analysis. We use NumPy for array-oriented processing, so it gives us matrices and tensors and these types of numerical objects that you need to store the data. And then on top of it, we use SciPy for all the algorithms and the signal processing, Matplotlib for visualization, and also a lot of scikit-learn, which I will show later to do decoding. So really, MNE sits on top of this very rich ecosystem and really leverages as much as it can. And also very importantly, since MNE was started, it was also the source and the foundation for new projects in the Python neuroscience ecosystem. MNE-BIDS, which I will illustrate in a minute, MNE-BIDS pipeline, which is also something I will come back to, but many more, MNE-IC label, which is a tool to automatically label ICA components using machine learning, MNE features, which is a way to extract handcrafted features from MEG and EEG to do, for example, machine learning. Auto-reject is a tool that was written in order to automate data curation and rejection of artifacted data. MNE-Nears is an extension of MNE to work with F-Nears data. And more recently, Brain Decode is a package that offers deep learning for EEG, MEG, and leverages a lot the internal MNE data structures. All right, so let's start by MNE-BIDS. So for those of you who have never heard about BIDS, BIDS is a way to organize your file in a very consistent and strict way. And MNE-BIDS allows you to take your original data, whatever the way you had organized them, and to structure them in a BIDS compliant way, but also to read it, manipulate it, and iterate over it. There's very rich set of tools that MNE-BIDS offer that I will briefly skim over. So BIDS, again, is nothing specific to MEG. BIDS is something that started with the MRI and medical imaging and neuroimaging community. Basically, MEG BIDS is an extension of the BIDS standard for MEG data. So I encourage you to read this paper, but also to read the current specification of the BIDS MEG standard to learn more how things should be done. And hopefully MNE-BIDS allows you to do many things without even having to read the documentation. All right, the MNE-BIDS pipeline, which I will also demo in a few minutes, is a way to automate the processing of BIDS formatted data. I would say automate probably 80% of the job, and therefore simplifying many of the analysis before allowing you to do the most, I'd say, advanced things that you may have to do for your clinical work or for your papers. And this is now also started to gain some momentum around the MNE community. All right, so the MNE-BIDS pipeline in a nutshell takes the BIDS formatted data. You run a command line tool, which I will illustrate in a minute, and you get a nice report that runs and gives you, for example, evoked plots like this or decoding results like this, decoding over time, but also automated source analysis, provided that the BIDS dataset is informed by so-called anatomical landmarks or fiducials in order to have the co-registration. And if you have this, you also can automate a lot of the source estimation process that you see here. So now this was a very quick set of slides, and now I will do some demo. But since I'm not sure I will have time to demo everything, I would like first to show you a few sets of videos that shows you how far we could go with the time. This is a nice video that shows you the co-registration UI that you can use in MNE-Python to set your landmarks and to adjust your alignment between your MEG headset and your anatomical surfaces and MRIs to compute the so-called head to MRI transformation. So you see here, you set the fiducials, you can visualize the location of the head shape points and the EEG electrodes, should you have any. You can also visualize the MEG helmet and make sure that everything is aligned properly. So this is what we called the MNE co-registration tool. Basically every dot that you see here, either, flat thing, either white or orange, is either a head shape point or MEG. And then you have the fiducials. All right, let me move to the next video. We also have a GUI to show you how to explore source analysis results. So this is the brain viewer, that's the way we call it. So here, this is a source estimate, distributed source estimate that was obtained using the DSPM methods, and you can explore specific locations by clicking on them. You can also obtain automatically the FreeSurfer annotations. So if you click on certain label from the FreeSurfer Atlas, then you get the time course at the bottom. So MNE is very much built on top of FreeSurfer for all the anatomical processing. So the segmentations and head model constructions and surface source space construction for surface-based source space construction. Right, so here, removing the atlas, going back to pure vertex-based activations. Okay. So that gives you a glimpse of the UI for interacting with source estimates. I said the recent one that was probably added over the last 2 or 3 years. Okay, so we'll be using public data for this tutorial. So we'll be using a data set that is available through the website called Open Neural. So we'll be using data set called the DS00248. And here I'm illustrating a command that you can run on your system, provided that you've installed the MNE software and its dependencies. You can here download this data set, and this will automatically download the files from Open Neural website. Okay, so it can take a few minutes depending on how fast is your internet connection. And this allows you to download some data, and the same data that I will use for the demo. Okay, so at the end of the day, if you've run the download tool, you should see something like this. Okay, so you have downloaded this, and then you're finished downloading, and now you can enjoy your brains. All right, I will show you this also in a minute. This is the so-called MNE bits pipeline that allows you to streamline all the processing from pre-processing, so Maxwell filtering, frequency filtering, etc., all the way to the report that I will also illustrate in a minute. Okay, so that's for the intro that I wanted to mention, and then I will do some live demo for the next 30 minutes. Okay, so let me jump into this tool. So this is VS Code, but this is just a way to create a so-called Jupyter notebook, and we'll use this for our tutorial today. All right, so you may be familiar with the standard Jupyter notebooks or Jupyter Lab, and this would be your way of working. Here, I will use this to also show you the power of such a text editor. Okay. All right, so I've copy pasted a few lines already to get started. If I look here, I've downloaded the data. So I've got this folder, so the DS00248 that contains a number of files. It contains, for example, the subject 001. So I've got one subject. It contains anatomical data, typically a T1 image, but it also contains the MEG. And this is the MEG file stored in a FIF file. And is a task called audiovisual, and we only have one run, and this is subject 1. Okay. You may also be curious about what this is. This is the corresponding empty room recording available for the same subject. Okay. If you look at the participants.tsv, okay, that gives you information about the participants. So for now, we have 2 subjects, subject 2.1, subject empty room. The age is not available, the sex or the handness is also not present. Okay. You can also have a dataset description. That's also a way to show you a bit more things about the bits standard. And you see here some information about the dataset. Okay, and I guess this is pretty much it for now. Okay, so let's get started. Here I'm gonna execute the cell, so maybe just restart the notebook. Okay, all right. So I'm importing NumPy and Matplotlib, but more importantly MNE. So the MNE-Python package for my analysis. Okay, so MNE has been imported, and I've got my row f names, which is the file name that contains my MEG. So what I will do is I'm going to read it. So here in row, you have a number of reading function that you have access to. Okay. So here I'm going to use something called read row fif, and I'm going to provide the row f name. Okay. So this will give me a so-called row object, and the row object is to corresponds to continuous, sometimes what is called continuous recording, and basically a FIF file that gets out of your MEG system. So if you just look at the info object in the notebook, it will show you a number of information. You will see what channels you have access to. So here you have 204 gradiometers, 102 magnetometers, 9 steam channel, 60 EEG, 1 EOG. 2 channels are marked as bad. You have 1 EOG channel, and you have no ECG. Sampling frequency is 600 Hertz. The data have been already filtered, bandpass filter between 0.1 Hertz and 172 Hertz with a low pass filter. There's a 3 SSP projection that were made available already at the acquisition. This is the file name. The data is 4 minutes and 38 seconds. And importantly, the measurement date is fairly old. It's even older than when MEG was invented, and it's because the bits data that we're manipulating has been anonymized before being shared. Okay. All right. So the first notion that MNE and I would like to cover is this notion of row objects. And every object or data container in MNE has this .info attribute. And the .info is what we refer to in MNE as the measurement info. And it contains also what you may call the metadata, or anything you would like to store that is basically specific to your recording. So it's a duplicate from what you've seen just before, but it's really a dictionary that contains a number of keys. For example, you can look at srec, so that would give you the sampling frequency. But you can also look at BADs. There would be a list of BAD channels. And you can also look, for example, at the projections. Basically, all of these information are part of the info dictionary, so the measurement info. All right, so let's do something that is fairly natural, which is to plot our data. And for this, you simply have to do row.plot. Okay. So this will start the new plotting UI that was contributed to MNE over the last few years. So it's a Qt-based browser that is extremely smooth and pleasant to use. So here at the bottom, you see different colors. Here, this corresponds to the planar gradiometers. Darker blue, they are the magnetometers. In black, you have the EEG. And if you go at the bottom, you see that you have all of the steam channels that are actually present. So you can move around in your data, okay, and fairly efficiently. If you press a number of key shortcuts, you will be able to do certain actions. If you're curious about this, you can just click here on the help button, okay? And what I will do is if you just press now B for butterfly plot, it will show you a basically a butterfly plot of all of the channels by channel types. And see if you move forward in time, for example, here you see something interesting. So if you click B again, this will move you back to regular plotting. And if you go down, okay, you should see here what we were looking for before, which is this flux jump artifact that is present in your data. Okay. So if you want to mark this window of data as bad, what you can do is the following. You can press on A, okay, for annotate. You can say you want to add a description. You're going to be saying it's a bad flux jump, for example. And now you can select a window, and this will mark you your data as a bad flux jump. If you click here, you see that some data are marked as bad. Okay, so you can click on their name to mark them as bad or not. And here you see that this one is bad. And at the bottom, you also have one EEG channel, which is a flat channel that is also basically bad due to a loss of electrode contact. All right. So many more things that you can do. You can change the duration of the page of the data that you're looking at. You can change the scaling. There are many things you can do. And I encourage you to look at the help to explore all this. All right, so let's close this. And once we have done this, if you look, you have here annotations that appeared on the data, and you see that it contains one segment, which is a bad flux jump that we've manually annotated from the data. Okay. So the next thing I would like to show you is how to plot the power spectrum density, which is something that is fairly natural to do. So here I'm going to look at the PSD of my data. Okay, and so this is what you get. You see the PSD for the EEG, for the gradiometers and the magnetometers. So here there's no obvious bad channels. All the channels seems to be fairly comparable in terms of the power spectrum density. And here the color is mapped to a specific location. So for example, one thing you can do is, for example, if you plot the PSD and you'd say that the maximum frequency that you want to look at is maybe 40 Hertz, that gives you a plot that is limited to lower frequencies. And then maybe you can select a specific frequency range, and that allows you to get a topography to know where you have some power in this frequency range on your different channel types. So I guess this illustrates the fact that there's a lot of MNE functions, although MNE, as you can see, is very much like a library and a scripting language, or script-based approach. Obviously, very comparable to things like Filtrip, the packages like Filtrip. So you have to write code, but most of the plots that actually you can produce are interactive, allowing you to interact with the plot and the data that you're manipulating. All right. So, and maybe one more thing, you can also click here on if you want to click on a line, okay, for example, here, you can see the name of the channel. Imagine that you have one channel which is very different from the other. You can click on the line to know what's his name to potentially mark the channel as bad. All right. All right, let's close this. So we've seen the notion of row object, but this is now basically the kind of the old way. I would like to show you now how to interact with the data through MNE bits. So basically what I call the MNE ecosystem. And for this, I'm going to import MNE bits and take an object here called a bits path and use the read row bits function that is now coming with MNE. All right, so my bits path is defined given the subject name, the task, the run, and then the bits root. So if you look at, if you look at bits path, okay, so it looks like this. And what you can do is do row, read row bits, and then you provide here your bits path. Okay, and now it's the same as before. You have read your data. It's the same as read row fifth, but now you've read your file through the bits path interface. Okay, so imagine that you had maybe another subject in your data. What you could do is dot copy, for example, dot update, and then do subject equal 02, and then by just doing this, you would now read the data for your other subject. All right, so since I have only one subject, I'm not going to do this. I just have my row object that I can now manipulate. Just as a remark, the raw data by default, they are not loaded in memory. Now I just loaded the measurement info and the metadata. If I want to load my data from disk, I now need to do row.load data. And now this is now will actually read the data and put it in memory. All right, so I've got my row object. I could do plotting the same way as before. It doesn't change. It's still the row object from ME. All right, so now let's look at continuing our exploration of the different MNE concepts. I'm going to introduce the notion of epochs. Okay, so let's see how to obtain some epochs. So if you do MNE.epochs, and if you do question mark, that will give you the doc of this. So epochs gets created from row object, events, some event ID, tmin, tmax, baseline. Okay, so let's understand what this corresponds to for us. So we have our Steam channel, which means that they tell us when the stimuli occur. So for this, I need to find the events. Let's do this. I'm going to do events, MNE.find events of my row object, and this will give me when are the onsets of my events in the data. Okay, now I need some event ID, which tells me what event corresponds to what. Okay, so for this, I'm going to copy it from my notes because that's otherwise a bit cumbersome to type. So I get event ID, auditory left, right, visual left, right, and this basically describes the events of interest. Okay, so I will do epochs, and I'm going to do row events ID equal event ID, events equal events, tmin equal, I'm going to do like this, tmax is going to be like this. I'm going to put a baseline. The baseline is going to be from none to 0, so basically from tmin to t0. And let's see. All right, so I made a mistake somewhere. Oh. All right, so here I've got my epochs, and I can actually also load them, and let's see if I can plot them. Okay, so it is now plotting me my epochs, and if you look a bit, so I can still click on the butterfly, and you see, for example, you have a bunch of epochs which are typically bad due to very strong amplitude of artifacts or a blink or whatever. Okay, so here there was no rejection, there was no removal of any epoch due to badness or artifacts. So historically, what MNE allows you to do is to reject based on peak-to-peak amplitude. And for this, I'm going to take this reject dictionary. Okay. So now I will reject epochs for which the peak-to-peak of the mags exceeds this value, or the peak-to-peaks of the EEG exceeds this value. All right, so let's do this. Reject equal reject. And also something that I'm going to, all right, let's maybe later. Let's do this. So now I'm going to reject. So you should see that the strong artifact is gone. And if you do a epochs.plot drop log, okay, it will show you that 17% of the artifacts of the epochs were dropped due to a strong amplitude on EOG. So that's obviously a blink, or certain times due to an MEG channel. Okay, so let's just do this. Okay, so now I've got epochs which are reasonably clean, and I can see how to proceed. So let's look at my epochs. You see that my epochs contain a number of conditions. Okay, so auditory left, auditory right, visual left, visual right. And what you can do is select the epoch that you want to keep. So for example, if you do epochs auditory, they will keep all the epochs which are either auditory left or auditory right. If you want the auditory left, we can do this, and that would be auditory. So now I've constructed or basically selected the epochs which are corresponding to the condition auditory left. All right. So now once you have this, you have your epoch selected. What you can call is the average methods. And if you call average, what you will obtain is a new object, which is actually an evoked object. So I'm going to call this evoked. And here you have evoked. So evoked contain 366 channels. They are basically the MEG plus EEG channels. And a number of time samples. Okay, so let's do this. I can do epochs and then plot it, and let's see what I get. All right, this is the evoked plot. And you see that since you have channel location, automatically you have the colored lines. And what you can do, again, this is interactive. If you select a specific time window, you see the different topographies. So here you see very nicely a dipole on the auditory cortex on the magnetometers. You see a strong energy also on the root mean square of the gradiometers, and also some signal on the EEG. Okay, you can do it slightly after, and you can have multiple of these at the same time. And this gets synchronized with the figure in the background. When you close them, it just removes this on this plot. Okay. All right, so now you've got your epochs, your evoked object. So you may wonder, okay, what can you do with these objects? You can see that you have many things that you can do with the object. So if you use your like VS Code or a good text editor, you will immediately see what you can do with this. And I like to explore what you can do with this. And maybe one thing I will try to illustrate now is this. If you do evoke.plot joint, you can click on the question mark, and it will show you the doc, okay? And see that all the parameters have default values. So you can just simply do evoke.plot joint, and this automatically produces this plot for the different channel types. So this is for EEG. This is now for MEG, magnetometers, and for the gradiometers, it produces automatically these types of plots. Okay. All right. So I promised to do a bit of machine learning and decoding in this presentation. So let's do this. So what I propose we do is we try to classify between two experimental conditions, like auditory left and auditory right. So we're going to do some decoding or machine learning. Okay. So I'm going to take my epochs for decoding. Epochs for decoding are going to be epochs that I'm going to limit to the magnetometers. Okay. Okay, so et voila. And if I now take the data, epochs.get data, and then labels, label equal to epochs.decoding of events Okay, so let's look at the data. I've got a number of epochs. So actually, I should only do auditory. Okay, so I've got 114 trials or epochs, and these are either auditory left or auditory right. I've got 102 magnetometers, which have been selected here, and this is the number of time points. So the game here is to classify between different conditions. So you see that you can be either a condition 1 or condition 2. Condition 1 is a left auditory, and condition 2 is a right auditory condition. Okay. So for this, I'm going to take some code here that I had written before. So from MNE decoding module, I'm going to take a vectorizer that would construct features which are all channels at all time points. This is for later. I'm going to use a scaler to scale the input before passing this to logistic regression. And I'm going to use this cross-val multi-score for evaluation. Okay, so this is now using scikit-learn, the pipeline, and a logistic regression to do the classification. So look at this, you have your classifier that is a scaler, a vectorizer, and a logistic regression. All right, so let's do this. Scores equal cross-val multi-scores. So let's do CLF. I've got data, label. I'm going to do a 5-fold cross-validation. And let's see if this works. Okay. So yes, it works. I obtained the scores, and you see that for the different split, different folds, you have different cross-validation scores. So what you can do is print cross-validation score, np.mean of scores. Okay, so the mean cross-validation score is 91, and I'm going to do std np.std of scores. Okay, so all right, so the standard deviation on the scores across the different folds. Okay, so this means that with 80% accuracy, 81%, you can classify between left auditory and right auditory using a simple logistic regression. So this is now taking as input all the time instance. And what you may want to do is to see when the effect occurs and do so-called time-by-time decoding in order to figure out where the effect of interest is actually in the data. So let me just take that code snippet I had written for this in the interest of time, because time is running fast. Okay, so I'm going to do this. All right, so what I'm going to do here, I take still a logistic regression, a standard scaler from scikit-learn, sliding estimator, which is doing the time-by-time decoding. And here, using a raw KUC scoring, obtain the scores. And this is now doing the same cross-validation, but now doing it over every time. Okay, and what you see here, that this is decoding score over time, and you see that by taking the data on the onset of the evoked components or the downside, basically due to the latency of left and right, you have some strong decoding scores. So basically before 100 milliseconds, you can almost decode with 90% accuracy each of the two conditions. All right. So I guess this is just a very quick overview of what you can do with MNE. I'd like to say a few words on the MNE bits pipeline that kind of allows you to do a lot more things than this. So for this, I'm going to open this config file that we have here. Okay, so this is a config file for the bits pipeline. This is the data that you're working with. This is the bits root. This is where you're going to put the derivatives, basically the files that the pipeline produces and outputs. This is where you have your subjects reconstruction that you obtain with FreeSurfer, the subject name, the different conditions that you want to consider, which conditions you want to contrast, including in the time frequency domain. If you want to run max filter, if you want to run max filter autobad to find the bad channels, the epochs Tmin, Tmax like we've done, the baseline. If you want to compute the noise covariance using here pre-stimulus data for source analysis, if you want to denoise using SSP vectors or projection vectors, etc. And here at the end, how many jobs do you actually want to use for processing? And here I'm going to just run over one job to see what you get. So kind of the idea is that you've downloaded your bits dataset, you've written your bits config file, and what you can simply do is MNE bits pipeline -- config and then the config file. You type enter, and this will run the bits pipeline on your data, basically reading your config parameters that you've just written. So this takes basically, of course, a few minutes to run on your data sets. So this is just to illustrate. So, okay, you see that it's computing. So here, actually, a lot of the computing that's already been done, this is why it's going fast. It's using some caching mechanisms to avoid recomputing anything that has been already computed. So I just interrupted it. And then once you're done, it produces a report like this, which is an HTML report that you can explore to see and look at the output. So this is the, for example, the roll plot of the input in butterfly mode. You have the power spectrum density, which I just showed. You have here the output of the autobad procedure to find which channel are bad and when. You can look at the bad channel also so this is the empty room data. You can look at the data, for example, after Maxwell filtering, etc. You can look at your events to know when you have some conditions arriving in your data. This is the event plot from MNE that you can do with MNE.plot events. You can look at your epochs before cleaning, how many conditions you have in different conditions. And I guess you can then look at your evoked objects. So this is the evoked plot that we've just illustrated together of the condition, which is the auditory condition. You can do the same with the visual, auditory left, etc. And these conditions, they have been defined here in this list: auditory, visual, auditory left, and auditory right. You also have the time-by-time decoding later. So this is the contrast between condition. The time-by-time decoding is illustrated here. So this is showing you across different polls what's the performance that you get. And you see, for example, that decoding visual versus auditory is almost perfectly done at the single trial level using MEG data. This is what you do when you do auditory left and auditory right, which is obviously a bit harder. You have the decoding time by time, okay, when you see the decoding power over time of auditory versus visual, auditory right versus auditory left, which is pretty much what we've just done briefly together, but now illustrated in a bit nicer way. And you also have a number of steps that I had no time to illustrate, which is in source space analysis. So you see the covariance that allows you to look at typically the noise that you will consider for source analysis. The BEM that you obtain with FreeSurfer. The co-registration outputs. So you see that the image, the MRI has been anonymized, so you can make sure that your co-registration is actually correct. You have the forward solution and also the source estimates. So here you have, for example, the auditory output using DSPM that you can just browse like this. This is not completely interactive. You cannot click here, but it allows you to very quickly check if you have an issue, and this really comes automatically with the bits pipeline. All right, I guess this is pretty much it. I will just conclude by bringing you to the MNE Tools website. So if you go here, you have a number of entries that you should look at. So the install page that I've briefly illustrated. You have the main documentation that you can explore. You have tutorials, you have a lot of examples. You have an API reference. So for example, if you want to, I mentioned this find events that we had. So if you have find events, you can find the documentation of find events. And if you go at the bottom, you will see all the examples that use find events. Let's take the first one. Okay, so we can just go to this page. And if you want to go to this page, you can, of course, read it. But very importantly, at the bottom, you can simply click download the Jupyter Notebook. And if you download the Jupyter Notebook, you should be able to run it on your machine and replicate all of these images that you see in the notebook. The search is also working pretty efficiently. You can search for keywords or information in the web page, and that should orient you correctly. All right, I guess this is everything I had to say. Thank you very much for your attention, and I'll be happy to take any questions you may have.
Hi, so we are now in the Q&A portion of the masterclass. So I have a first question for Alex on when we can just get his audio up. Just 1 second, if you can bear with us, please.
Yes, can you hear me now?
Yes, hi, we can hear you, perfect. So one of the first questions that we have for you, and also for everyone that's listening right now, I suggest if you haven't already, you look at the chat, because throughout Alex has been responding to some of your questions with links and files. So definitely check that out if you haven't already. So one question is, can the BIDS pipeline also be used on resting state data and where there are no specific events or trials? Thank you.
Yes, we've used the bits pipeline for rest data, the context, for example, of brain age prediction. And so you can, there's a config parameter in the bits pipeline when you say that the data should be considered as rest. And in this case, the epochs are constructed typically by windows of 10 seconds or sliding windows of 10 seconds. So you chunk the data in 10 seconds windows, and you can ignore the events.
Great. Another question that we've had is, thank you for the amazing talk and demonstration. Could you please tell how to save pre-processed data and annotated data for later use?
So if you have raw data, you can just do raw.save, and you will save typically as a FIF file your data and the matching annotations in the same file consistently.
Okay, another question is, I am using Spider, but some of the plots are not interactive.
This should be fixed and can be fixed. I encourage you to visit the forum, the MNE forum, to ask these questions, and I'm sure someone will give you some hints to fix this.
Okay, another question that we have is, can the automated source estimation be executed for EEG data when we have no MRI or individual anatomy data? Thank you.
To be checked. I think we've done this also with brain age using, if you have electrode templates and you would do the source reconstruction using FS average. So I would say 80% sure it's possible, but to be confirmed.
Okay, next question. How can one plot the connectivity matrix, not the circular graph, but the, in quotations, square connectivity matrix between parcellations? Thank you.
There's no built-in functions to do this, but if you just do a pyplot.matcho or a heat map in Seaborn, that's quite easy, I would say. So the MNE connectivity, which I did not mention today. So historically, MNE had a connectivity submodule, which we moved out, and now there's a specific package called MNE connectivity that kind of enriched and took over all the connectivity implementations. So you can ask a question on specific to MNE connectivity on this repository. So Adam Lee is maintaining this. And if there's no example to do this, you can ask for it, and I'm sure he will add it.
And then another question is how to do batch processing. And we still have time for Q&A, so if anybody would like to continue to put questions in the chat, we're happy to answer. Thanks.
So I'm not sure what you mean by batch processing, like processing on the cluster.
The question hasn't specified, so hopefully if they have further follow-up, they can write in. In the meantime, that's it in our questions. If there's anything, Alex, you'd like to address that.
So maybe assuming that batch processing is running at, like on the cluster. So the bits pipeline, there's a lot of lot of functions of MNE-Python have this end jobs parameter. When you do end jobs equals something more than one, it will use multiple CPUs on your machine. And so the pipeline has an end jobs parameter. And for example, when we process CamCan using the bits pipeline in the at INRIA, in the INRIA team, we put end jobs equal 40, and we process 40 subjects at a time on one big desktop machine.
Okay, we have another 2 questions that have come in. So one is, hi Alex, thank you for the great talk. Is there any integration between the virtual brain, TVB modeling environments and MNE-Python? For example, is it possible processing stimulated data from a TVB model with MNE-Python? Further, are there plans to integrate TVB and MNE-Python in a deeper way in future?
Good question. I've never worked with TVB myself, but the name that comes to mind is Marmaduke, is an engineer working in Marseille on the TVB and has a lot of experience with MNE, and I'm sure he has done something like this, but I would orient you towards the TVB people because they use a lot of Python code and they've used a lot of MNE code historically. So I'm sure there's some code somewhere to do what you ask.
Okay, thank you. This audience has been amazing in terms of sending in questions. So we have a few more that have come in. Is there a tutorial on kurtosis beamforming on resting state data?
Not that I know of, and I did some implementation of this in the past on typically epilepsy data, and so the kind of the short answer is every time we build a tutorial, we need the data sets to make a point and to show that this code is doing something reasonable on real data and is being practically useful. And if you want such a tutorial to be, for example, relevant for clinical work with epilepsy data, if you can point us to some public data sets, or if you can share some data with us so we can build a tutorial that that demos kurtosis beamformer, I'm sure, I'm not saying it's going to be done over the weekend, but it's reasonable to expect that over the next few weeks or a couple of months, somebody will give it a try. So please share your data, even if it's clinical data, if you can.
Great. Do you foresee any issues with running OPM data through MNE?
Excellent question. There's been a recent push on OPM. So historically, if you look on the MNE, so I guess I could probably try to show my screen. All right, I guess. Do you see my screen now?
Yes.
Okay. So if you look at OPM here, there's an OPM dataset here that was contributed by Lauri Parkkonen in Aalto. And so there's an example of working with OPM data that have been exposed through FIFA. And so there's data you can already play with. So it's a tutorial, you can just download it at the end. And I know that the people at the field also, that's not at the field, at UCL, working with OPM and George O'Neill, I think, and with the help of Eric Carson, have recently contributed some code in MNE-Python. It's not released yet, but to support the OPM data that they produce, and they typically work in the lab, they use in their lab. So there's some efforts to do this through data sharing and building tutorials or making sure that MNE can read the format that these systems are producing.
Great. So are there any limits to running MNE-Python on Windows?
No. We'll have plenty of Windows users. I would say the only pain point you may have is that for all the anatomical pipeline, we use FreeSurfer. So it means that to do the segmentation and what we call the MRI reconstruction, you need a Mac or Linux machine. But once you have basically run MNE.ReconAll FreeSurfer ReconAll or on your MRIs, and you have the output of FreeSurfer, then you're completely fine working entirely on Windows.
So another couple questions have come in here. As you know, one is asking, as you know, the Julia programming language is also becoming more popular in scientific computing. Do you think we might need an MNE Julia in future?
So MNE-Python took 12 years to write. So there's an MNE MATLAB code, which is basically just to read FIF files in MATLAB. So I guess I would be happy to see this happening, but if you want to do this, be ready to work for many, many years to get something at the level of MNE-Python.
Do you have any comment of MEGIN specific data like rank reduced data after SSS, whether or not to use gradiometer and magnetometers combinedly? Thank you.
So MNE typically works always with combined MEG magnetometers and gradiometers. I mean, MNE has a very good support of what we call channel types. So it's completely easy to have in one raw objects, EEG, MEG, EOG, gradiometers, magnetometers, EMG. I mean, you can put all this in one file, and MNE is pretty good at understanding that there are different things compared to other packages which are historically pure EEG, where the notion of channel type is not like a first-class citizen. With MNE, you can really have a very clear control of channel types, and this allows us to automate and to make the right decision when we have combined channels. And typically, therefore, MNE allows you to do, for example, a beamformer using combined gradiometers and magnetometers, and that's not an issue.
So is it possible to get the latency values, amplitude values in a CSV or JSON file?
That's it would be evoked.get data and then 2 lines of NumPy code and then 1 line of pandas code to write in CSV. So I mean, when I say this, it might seem a bit complicated, but it's kind of a trade-off. How much MNE gives you 1-line solution to do every possible use case? I mean, to be able to use MNE-Python, you need a bit of background knowledge on NumPy, and you need a bit of background knowledge on the scientific Python ecosystem. And so I think that's a bullet that you need to bite a tiny bit. It's like in MATLAB, if you want to work with MATLAB, you need to be able to work with matrices and these types of things. So I guess there's no free lunch. You'll need to learn a bit more in the basics of the Python programming language, and there are plenty of videos and tutorials to do this.
So I think that is our last question. Thank you so much, Alex Gramfort, for being our presenter today, and thank you everybody for joining, and we hope to see you all again on future masterclasses. So thanks again, everyone.
All right. Thank you very much. Thank you.
Bye.